Okay. There I am. You see this picture of me? This picture of me was taken in, I think, 2008, maybe. And I just keep using it because I hate getting my picture taken, thinking, it's close enough. You know, so it's one of the only ones here. So yes, here we are. Now we're live streaming. So welcome back. Given that we're going to have a few people missing today, I decided to bump Lecture 7A to next week because that's more, I would say not more important, but it will make more sense when Lecture 7B follows it immediately. What we have to do for now, for the next few classes, is actually move backward temporarily. The idea that's coming is that we're going to start adding in time-invariant predictors into our longitudinal models. And what you're quickly going to find is that when we do that, every fixed effect that we'll have to interpret, almost every, is going to be an interaction of some kind. And I had taught this class for years and years where I was trying to teach people that concept of how to interpret a time-invariant predictor. At the same time, I was trying to teach them how to interpret any kind of interaction. And I found that people struggled at trying to do sort of two new things at once. So what I decided to start doing is just back up and talk about interactions just in regular cross-sectional regression models, and then talk about them in the context of longitudinal, in which we have more things to worry about in terms of complexity. So do you remember the quiz that or not a quiz, I gave you a survey to get into this class, and I asked you about interaction terms? Do you remember that? Mm-hmm. You guys did really well. The people, I was really pleasantly surprised. So it may be the case that this is easy for you and we could zip through it, and it may be the case that we need to spend time on it. I don't really know, but we will find out. So that's what we have to do. Before we dive into that, though, any homework questions?
I have a question.
You do? Okay. Test statistics. Let me log in. We will log in.
Also have one.
Okay, great.
Question 20.
All right, and you're in homework 5. Question 20.
Yeah, section 3.
Mm-hmm. Enter the test statistic for whether there is significant variability in rate of change per month. Okay.
What kind of test statistic? You said that don't look at p-value.
Well, so a p-value is not a test statistic. A test statistic is something like a t, a z, an f, a chi-square, something like that. So it's one of those letters.
Actually, I tried everything.
You tried everything.
Yeah.
So the question then I would have is, what is it the test statistic for specifically? So what I'm looking for here is for you to link sort of these more Englishy terms, sort of lay description terms, with the statistical term that goes with it to make sure that we're talking about the same parameter in the model. So whether there is significance, that part is just covered in the idea of test statistic, because that's what the purpose of the test statistic is to tell you. But what we're testing is variability in the rate of change. So what do you think of when you think of variability? In this context, what am I talking about? Random effects, right? So which random effect? Significant variability in the rate of change per month. Which random effect am I talking about? The linear time slope. So how do I know if I have a significant random linear time slope?
It's one with a fixed difference.
It's a model comparison. And we are in REML for this assignment, right? So you don't have to worry about which kind of ML or REML. So it's a model comparison against a model without the random linear time slope, in which case it's a -2 log likelihood difference, right? That difference is supposed to be distributed as a chi-square. Does that help? And I say supposed to be because it's the mixture chi-square thing that I told you I couldn't care about, but I wanted you to know about anyway. So you can use just a regular 2 degrees of freedom for that. Yeah, okay, so 24 is next. Are you good?
The test statistic is chi-square.
It should be a chi-square. From a model comparison. Okay, 24. Enter the t-test statistic. So that one I gave it to you, right? T-test. For the improvement in model fit relative to the last model. So this is referring to this idea, right? So you have added a new term, adding a common rate of change in the linear rate of change. So you figured out what that is?
Fixed quadratic model.
Yeah, that's added a fixed quadratic effective time, right? Yep. Enter the estimate for it. You got that far?
Yeah.
Okay. Where you found the estimate, go over 3 columns.
The t-test is for the quadratic estimator.
For the quadratic fixed effect, yes. Yeah, so improvement in model fit is another way to think about it, right? If you add a fixed effect and it's significant, you have improved your model.
Okay. Oh, yeah. I did a model comparison using FL.
That also would be a correct thing to do. However, you run the risk of having an incorrect standard error for your fixed effects because you're in ML rather than Rho. So generally speaking, you don't want to switch estimators to answer a question. But this is just another way of phrasing it. What does significant mean? Well, it means you made your model better. At least that's what I think it means.
I used the ML model comparison, and I got the correct answer for the p-value for number 25. But the p-value is incorrect because initially I inserted the chi-square. Then I was thinking, how can I transfer chi-square to a t-value? I know. So t is to f as z is to chi-square. So t squared is the analog to chi-square, but then you also have to account for the numerator degrees of freedom. In this case, there's only one, so you don't have a different value. But normally, f times numerator degrees of freedom is chi-square, if I remember correctly. I sometimes say it backwards, but there is a one-to-one relationship. So yeah, if you did not have denominator degrees of freedom being estimated, then this is a z instead, and z squared is chi-square. Yeah.
So it all fits together. What? T squared is f, yeah. F is the same as chi-square if you have 1 degree freedom. The difference is the reference distribution that gives you the p-value for it. Sure. Other questions? And for those of you who don't have to do your homework, you have an account if you ever choose to use it.
Yeah.
Just saying. I understand that you may not want to, but if you really want to learn this stuff, this is forcing you to interact with the material. So just putting that out there. Other questions? No? Okay, let me go to my live stream. Ishmael is here. Hello. No, I'm saying it wrong again. Ismail. Sorry about that. Do you have any questions? See if he answers. There's a delay. Huh? Well, I'll check back in a minute or two and see if he has any homework questions. Otherwise, we can go into the stuff for today. Interactions. Okay, so let me ask you this. When you took your regression courses, or whatever courses you took, you didn't have regression here, right? It's like a sort of first-year statty kind of course.
Yeah, for that one, yeah.
Yeah, okay. Has anyone ever taught you how to interpret interaction terms in linear models? Let me just ask you guys that. Yes. How did they teach you to do it? Controlling for? Just changing the language? No? Okay, well, we'll see. We'll see if the way that I need you to be able to do it is the way you were taught it. Because you may have been taught differently. So then it's the same as not being taught in terms of where I'm headed. But historically, I have found that people vary a lot in whether or not this was covered or how it was covered. Typically, in the context of an ANOVA class, all of the interactions are estimated by default when you run an ANOVA, like a factorial design, whereas in regression, you have to put them in yourself if you want them. And so they tend to be emphasized a lot more in analysis of variance courses than they do in regression courses. But I need you to be able to do it no matter what kind of model it is. And so we'll go first in the context of regression type models, where all of the predictors are continuous, and then move into a mix of continuous and discrete predictors, and then all discrete, which would be sort of an ANOVA. So we'll jump in to this lecture, which is 2B, like I said, backing up because it goes with chapter 2. So, ready? Yes. Okay. And no questions from the folks at home, or the folk at home, as it were. Okay, so interaction terms. This is the idea of addressing hypotheses about moderation. It's just the idea that the effect of a predictor depends on the value of another predictor in the model. You can always interpret interactions between any kind of predictors. Whether or not they get included by default depends on the type of model it is and how you're asking for it to be estimated. Like I said in ANOVA, if you have discrete grouping variables, the default specification is full factorial, where you have all possible interactions. And people typically don't remove non-significant interactions. They just interpret the full model as it is. In ANCOVA, if you include continuous predictors, they're not supposed to interact with the grouping variables. Otherwise, that's called a violation of homogeneity of regression, although there's nothing wrong with putting the interactions in if that's what the case needs to be. And then in regression, it's totally up to you. And most regression software forces you to create a new variable for the interaction variable ahead of time in your data set, and we don't have to do that. So if you wanted an interaction term between centered X and centered Z in mixed, we can just type that with the asterisk, the same as we did time by time. It's the same idea, which is nice. All mixed modeling software packages allow you to do that in some way, shape, or form. It just depends on what the connector is. So the idea of a two-way interaction is that it does something to the main effects of the predictors that are part of the interaction. So we have to have the main effects in the model. You know that, right? Someone drill that into you. If you have an interaction, the main effects stay no matter what. Good. And it's because they become conditional main effects. And so this was, I think, your very first homework in the online system was focusing on vocabulary for this, conditional versus marginal. And everything at the time, it was homework 2, I believe, that model had only main effects of predictors, and so all of the main effects were marginal. You could just say, this is the effect of X for everyone. This is the effect of Z for everyone. If we have a model that looks like this, so I have a predictor W, a predictor X, a predictor Z, and an X by Z interaction. In that case, I would call the effect of W, I would use the term main effect or marginal main effect, because it would say the effect on Y for a 1 unit change in W is irrespective of your values on anything else. In contrast, the effect of X is conditional. It is incorrect to talk about the effect of X as a unitary concept. The effect of X that is going to be given to you by the model is specifically when Z is 0. If Z is something else, it's a different effect of X that is implied. And likewise, vice versa, the effect of Z is specific to the 0 value of X. And so this idea of holding constant, you said that word earlier, right? Yes. So this is a frequent source of confusion. Whenever you have multiple predictors in a model, regardless of whether they interact, you can say that this is the effect of W holding constant X and Z. But it's the same effect of W at any level of X or Z because they don't interact. So this new conditionality that I'm talking about is after controlling for W and Z, we have the effect of X. But the effect of X is after controlling for and specific to Z equals 0. It's another layer of conditionality. So it's not just holding constant. Holding constant at 0. Does that make sense? Maybe? Everything is holding constant. Like that language applies whenever you have more than one predictor. This is holding constant at a specific value. The interaction term implies that the effect of x would be different if z equals 1 or if z equals 2, and vice versa. So here's some practice and why it's important to center our predictors. So centering is a very big deal to me. I always center my predictors even when it actually wouldn't matter, because I always want to have a fixed intercept that means something. It becomes even more important when we introduce interactions among predictors in the model, because we want our main effects to be conditional on reasonable values. So let's do this together. The 4 of you get to do a whole lot of participation today. How's that sound? Yay! Do you know what I call participation? Learning. You get practice. How do you get better at something? Practice. Or as my husband would say, perfect practice. That's apparently a baseball thing or some sports reference, that you have to practice perfectly, meaning technique matters. I think that's what that means. So we'll engage in some perfect practice. So here's my model. Let's say that I have trying to predict student GPA on a percentage scale as my outcome as a function of parent attitudes about education. So this is, let's say this is an average on a 1 to 5 scale across items. And I'm also controlling for the father's education level as measured in years of schooling. And I just put attitudes and education directly into the model. I don't do anything to center them or transform them. I just put them in as is. And let's say that the software returns these fixed effects. So we're back to regression, right? This is just a cross-sectional example where people are independent, no longitudinal. So 30 is my intercept, right? According to this. What does it mean? 30 is my expected GPA for what kind of person? Hold the others holding at 0, so walk it through. For somebody with no attitude on the 1 to 5 scale, not possible. Yes, exactly, that face. He's like, eh? Like, exactly. So for someone who doesn't exist so far, attitudes of 0, and
no education,
a father who'd never even been to kindergarten, right? Could happen. It's unlikely that in a research study you would find somebody like that. So we'll say expected GPA when attitudes is 0 and education is 0. Okay. Beta 1 is 1. So this is the slope for the effective attitudes, right? So we know what a slope is. Change in y for 1 unit change in x. So we'll say expected diff in GPA per unit at, am I done? Or do I have to keep typing?
you have to keep typing.
Got to keep typing, because this is not just a main effect. This is a conditional main effect, or what is known as a simple main effect sometimes. When
Father's education is 0.
When education is 0. Likewise, beta 2. Expected, I can't spell expected that way. Expected diff in GPA per unit ed. ... Harry, your turn. Yeah, your turn.
Attitude is 0.
Yep, when attitude is 0. So far we are 0 for 3 in model parameters that actually mean anything given the sample that we have. That's not good, right? What's the point of estimating numbers if they're useless? Now, last one, interaction term. Now we get to something that is potentially useful. And we have 2 different ways that we can talk about it. Both are equally correct. Which way that you would decide to talk about it is going to be dictated by the research questions of your study and the context. Typically, we view one as the focal predictor and the other is the moderator. There is no numerical or statistical way to say which is the moderator. They both work that way. So if my study was all about the effects of education in student outcomes, or parent education and parent expectations, let's say that that's my study, and I wanted to see how the effect of education varied as a function of a parent's attitude. Attitude is the moderator. So here's what I'm going to do. We're going to start with education. Ed slope is the unit of discussion here. All interactions fall into one of four kinds, and you've already learned them. More positive, less positive, more negative, or less negative. So we take the main effect that we're starting with here, which is Ed slope, which is positive, and it becomes more positive, because this is a positive interaction coefficient, by 0.5 per level of attitude. So I'll say Ed slope more pos by 0.05 times attitude. If I go the other way, if my study is all about the effects of parent attitudes, and I want to ask how the effect of an attitude varies as a function of their education level, now it's the attitude slope that is the focus of interest, and what happens to it according to the interaction. Yeah, well, it's positive, so it's either going to become more positive or less positive. And this is a more. More positive by 0.5 per
education.
Yep, this one's Ed. Yep. So what two-way interactions do is they change the main effects. They make them more positive, less positive, more negative, or less negative, depending on how they are to start with. So I can calculate for any level of attitude and education what the expected main effect is of the other variable. And I can calculate the predicted GPA for any kind of person. So in this case, if I wanted to fill in a prediction for somebody who has an attitude at 3, sort of the midpoint of the scale, and maybe their father graduated high school, so let's call that 12 years, I can take the model coefficients, stick in the values of the predictor variables for which I want the predicted GPA, and it works out to be 75 in this case. Cool. You can do this part, right? Okay, so did anybody teach you this? The more positive, less positive, more negative, less negative? You're like, maybe, a little bit?
I don't know if I remember it.
You don't know if you remember that. Fair enough. So we'll just pretend that no one ever told it to you, because then it's not their fault, right? Or your fault. So let's see what the model then tells us in terms of how to come up with the predicted slope as well as predicted values. So this equation right here can be decomposed to get simple slopes for either predictor as a function of the interacting variable. So what we have to do first to figure this out with how the model predicts these things is say, okay, if I want the effect of attitudes, right, and I want to make a predicted effect of attitudes for different kinds of people, I go up to my equation, and to start with, I have to pull out every term that has something to do with attitudes. So, not the intercept, yes, the main effect of attitudes, no to the main effect of education, but yes to attitudes by education. So then I'm right here. If you then factor out attitudes out of these two terms, you get to something that looks like this, right? So the terms in parentheses, this linear combination of beta 1 plus beta 3 times education, that gives you the slope for attitudes for any level of education. So not just the one that was given to you by the model, but any. The one that was given to you by the model is when education is 0, because that's the only time that the slope of attitudes is exactly beta 1. So let's try to see how this would work if I have a new reference point for the model of attitudes equals 3 and education equals 12. Okay. We have this, we're working this out here. So we did the expected value from GPA when attitudes is 3 and education is 12. On the previous slide, we found that to be 75. That would be our new intercept if we reran the model after centering our variables. So I'm going to put 75 here. 74. Close enough. Now, how do I know what my new slope for the effective attitudes would be? Well, my old one, which was beta 1, which was estimated as 1, the old one was specifically when attitudes, or excuse me, when education is 0, right? So how do we find it for some other value of education such as 12? Well, find the terms that have attitudes in them, factor attitudes out, and fill in the 12 where it belongs. So now, what does the model say the slope of attitudes is if education is 12? 7, yes. This is about all the level of math I trust myself to do in front of you. So it's good that we all converge onto the same number. See, for those of you out there who think, I never want a career in statistics because I'm bad at math, me too. Don't let it stop you. Because I'm good at programming. And if you're good at programming, you can make it do the math for you. You just have to figure out the logic. So let's go the other way. This slope of education of 2, this beta 2, is specifically when attitudes is 0. How do we figure out what it is going to become for attitudes of 3? Well, we do the same thing, but now with respect to the terms that have education in them. So education is the common thing here. I would say a root, maybe. It's the unit that we're trying to get the slope for. So we start with its simple main effect, and then how it varies as a function of the interaction term and the attitude level that we want to solve it for. So in this case, it's 3. Now this is the hard part, knowing when to put the value into the interaction term for attitudes versus the value for education. It depends on which is the moderator. So if what you're asking about is the effect of attitudes, the number that goes in here is what value of education you want the effect of attitudes for. If you go the other way, if you want the slope for education, the number that goes in here is for attitudes you want the slope of education for. So we can figure out, even without recentering, what the model-implied terms would be. So if I solve for this one, what do I put here? This math. 3.5. Now, the last one. What about my two-way interaction of attitude and education? What does it become, given that I have recentered attitudes and education relative to the previous model?
Stay the same.
Should stay the same. Why? Because this interaction is unconditional. There is no third variable that it is specific to. So it is 0.5 forever and ever, regardless of what happens to the main effects. So the purpose of centering your predictors is to create intercepts and conditional or simple main effects that actually mean something. But you can ask via estimate statements, which we're going to look at next, for what the model says the slope would be for any level of your predictors, not just the zero values that you happen to center around. Yeah.
But so that gives us accurate, or I guess interpretable estimates, but the model fit doesn't change no matter what we do.
And
in terms of centering.
Nope. The predicted GPAs, same. Variance explained, same. All of it. Once upon a time, there used to be people who'd cry about collinearity or multicollinearity as a reason to center. No, that's not a thing. Modern day computers, there's no reason for that. If you're dealing with older technology where things were more numerically unstable, maybe, but no. Centering is all about interpretation.
And that's why you don't do like the exact center, you center at a particular meaningful bit.
Yeah, I mean, you could put this at the mean education for the sample, or the mean attitude. Any number is just as good as another. I like reference points that are, I can think about a real person, because a mean is a sample-specific statistic. And like, what is mean education? In some samples, it might be 8th grade. In some samples, it might be a master's degree, right? So I like the idea of like putting education at 12 years or 16 years or something that is like, this is like someone who has a bachelor's degree. I guess maybe that's 17 nowadays. But how long did bachelor's degrees take you guys? I did mine in 4, but I did a lot of summer school to get that done.
4 years.
4 years also? 4? 4? 4. Okay, 16 it is in this class. Good.
And paying for it in grad school.
And paying for it in grad school. Yeah, see, do you know how I paid off my student loans? Doing workshops. You learn this shit, someone will pay you not only to do it, but to teach other people. I don't have student loans. I did workshops and paid them off. That's what I would recommend. And then I got tired of doing workshops and I gave them to my grad student. And so now he's paying off his loans. So, moral of the story, statistics equals money. If you can learn how to program this stuff and if you can learn how to explain it to people, the latter is the most important, because that's where the rubber meets the road, is being able to actually explain these results. And so that's why I pound into you, what would this be in English, right? Because at the end of the day, people who care about your results need to be able to think about it that way. So we can do this. We can do it in our heads for simple round numbers like this, but what don't we get with these new numbers, just making them up? We don't get standard errors. And in order to assess whether or not they're significant, we need standard errors. So there are multiple ways to do that. The easiest, which is what I'm going to teach you, is ask the software. So we'll learn how to write estimate statements that give us this. Another alternative, and this is the way that I was taught, by the way, is to recenter your predictors. So let's say that you have a significant interaction of attitudes and education, and you want to know if the effect of education is significant for someone with attitudes of 1, 3, and 5. An easy way to answer that question is to run 3 models, each time with attitudes centered at 1, 3, or 5, because then the simple main effect of education will give you that effect at that level of attitudes. That's annoying to run the same model over and over again, right? No, you can write 3 lines of code for your one model and get everything that you need. Or you can compute the standard errors yourself. There are formulas. You can find them. I don't recommend this. There's several reasons I don't recommend this. Number 1, every time you change the model, the standard errors change and you'll have to redo your calculations. Number 2, numeric precision. When the program does it, it saves however many decimal places it needs to keep things precise, whereas you don't when you're looking at output. And number 3, you're likely to screw it up because we're human. So while there may be value in doing the hand calculations behind these standard errors for pedagogical purposes, I'm not going there. We're doing estimate statements. So where do these things come from? To get the new standard error, we have to ask for something called an asymptotic covariance matrix. It's the covariance matrix that describes the sampling variability of the fixed effects. So the diagonal of this matrix is the standard error for each squared, and the off diagonals give the covariances. So in order to calculate what the new standard error would be for any of these model-implied effects, you need these extra terms in here. And these terms are also used in something called regions of significance, which is another way to interpret interactions that I want to teach you as well, because I think it's super useful in practice. So, how are we doing so far? Good? Still awake? Still with me? And nothing from Ishmael. I keep saying your name wrong. I'm so sorry. Ismail. It's like I learned it wrong to start with, and it's always going to be wrong.
So that's asymptotic covariance matrix relates to the hat matrix, like kind of like inverse and then.
Yes, it's the Fisher information matrix, I think. Those words all belong in the same sentence, but I'm not sure exactly how. I'd have to look it up, to be honest with you, but yes, you're probably right.
I remember Dr. Camping mentioned the hat matrix when he was doing the linear model, Bayesian estimation for linear model a couple of weeks ago.
What is a hat matrix? Remind me.
It's the X matrix, maybe inverse, multiply the Y matrix.
Yes. That rings a bell. I have a tentative yes, I think that's the same thing. I will have to ask him when I get home. But yes, it's the standard errors that show up on your output next to the fixed effects. If you square those, that's the diagonal of this matrix. It's the covariance that doesn't show up on your output anywhere, covariance between the fixed effect estimates, and that's the extra thing that you'd have to ask for if you wanted to calculate this by hand. So, but it's in there, and so that's why the program can do this for you. So here's what this would look like if we were trying to get all of these things, these predictions that we just worked out in our heads from the software. So let's say that we have our original model here, uncentered version, and I want to know what the predicted GPA would be for someone with attitudes of 3 and education 12, as well as the simple effects of each slope conditional on the interaction. So here's my model. Y equals attitudes, education, and their interaction. So 2 different kinds of estimate statements here. Whenever you're asking for a predicted outcome, so synonyms for this include intercept, conditional mean, expected value, predicted Y. All of those things mean the same thing to me. Whenever you're doing that, you need the whole model, every single fixed effect in the model. Otherwise, if you omit it, you're assuming that its value goes to 0. So if I want to get the predicted GPA for this kind of person, I need 1 intercept. So what this refers to when you type intercept is beta 0, or what's going to be gamma 0, 0 back in longitudinal land. I need 1 of those. I need 3 beta 1s because I want beta 1 if attitude is 3. I need 12 education here multiplied by beta 2, so I need 12 beta 2s. And then 3 times 12 is 36. So that's how I would figure out predicted GPA. Now to get the simple slopes of the interaction term, the conditional main effects, simple main effects, simple slopes, simple main effects. All of those words mean the same thing to me. The idea that it's the slope at a particular value, particular value of the interacting predictor. There we go. Note what's not here. No intercepts. We're talking slopes. Slope is the thing we're trying to estimate. The intercept does not contribute to the slope. What contributes to the effect of attitudes? Only the terms that have attitudes in them. So that's why we start off with 1 beta 1, no main effects of education. This is here just for pedagogical purposes. If you don't write it, it's assumed to be 0 also. And then the value that we fill in for the interaction term is for the moderator. The other variable than the one that you're asking for the slope for. We want the attitude slope when education is 12. That's why it's opposite on the last line, where what we're asking for is the education slope. Now attitudes is the moderator, and we fill in 3 for its value for the interaction term. Okay. Little bit of practice. So if we want to predict GPA after recentering these predictors, so if attitudes is centered at 3 and education is centered at 12, and I want to get predicted GPA for attitude equals 5, what goes here, where my cursor is? What goes here? And don't say 5. Not a trick. Huh? What? Say it. 2, yeah. It seems obvious, but people forget when they center variables that whatever predictions you plug in have to be relative to the centered variables for it to make sense. I've seen people screw this up frequently, so I don't want you to be one of them. What goes here if we want the value for education 16?
4.
It's 4. What goes here? 8. Yes, 2 times 4 goes here. Yep. So you get this concept, right? Okay, we'll move on. Next, practice getting predicted slopes. So, model has been centered. Attitudes 3, education 12. Now we're asking for simple slopes for different levels of the interacting variable. Note I have helped you out here by saying intercept 0 for all of these because we are talking slopes. What goes here? I want the attitude slope if education is 10. So when I say attitude, what I'm actually referring to is beta 1. How many beta 1s do I need in forming the attitude slope? 1. So when I say, give me the attitude slope, that's all the further you have to listen. You know immediately that's what we want. The term that we want gets a 1. So give me the attitude slope, 1. If education is 10, what goes here? This word, education, refers to beta 2. What did you say? 0. Now let's think about this. Wait, because people are like, no, it's education equals 10, right? And you want to put a 10 there or something, but no. It's a main effect. The main effect of education has nothing to do with the attitude slope. The only terms that are going to be non-zero in this line are things that have attitude as part of them. So that goes to 0. Now what goes here? It's the now we need to know if education equals 10, and then say what is 10 relative to my new centering point? Minus 2. There we go. Next one, what goes here? If now we want it for education equals 18. Still be 1. Still be 0. And what goes here? 6. So you guys are good at this. Now, down here, other way. Now, attitudes is the moderator. What we want is ed slope. What goes here?
0.
Zeros, yes. The main effect of attitudes has nothing to do with the ed slope. What goes here?
1.
Yep. And 1 for this one. And what goes here?
-1.
-1. What goes here?
2.
This is the hard part. Same term, different value. It's the value for the other predictor, the one that you're not asking for the slope for. No, that was a clumsy sentence, but that's the best way I can explain it. The other one. Okay. So here's a little more practice with this concept, now changing it up so that we have a dummy code as one of the predictors, men versus women, which in my little example here is a binary variable. So let's say that we have a model in which we are estimating the interaction of age and gender. So if I wanted to talk about the effective age and what is the effective age as a function of gender, gender is the moderator, what goes here? 1. What goes here? 0. Main effect does not get anything. What goes here? Yeah, the coding is up here. Yep, it's 0. And that means if I want it for the other group, need one of those, none of these, and what goes here? 1. So with respect to the age slope, there's only 3 things that we would want to know. Is there a significant effective age for men? That's what the main effective age in the model is going to tell us already because men are the 0. Is there a main effective age for women? The model does not tell us that, but we can find out if we add the slope for age to the interaction term for the slope with women. It's a linear combination. That's the missing piece. And then the last part, is the age slope different by gender? Do we know that one?
That would be 3.
That is beta 3. So if we recentered gender such that we flip the reference groups, then the model would tell us what is the age slope for women. That would be beta 1. Does it differ for men would be beta 3. And what it is for a man would be beta 1 plus beta 3. So in that case, your job is pretty easy in terms of explaining an interaction term if what you care about is the age slope and you just want to talk about what it is for different kinds of people because there's only 2 possibilities. What if we went the other way? What if we're focusing on gender differences and age is the moderator? So age is centered at 85 in this example. What goes here?
0.
This is the 0, right? This is the main effective age, not relevant. What goes here?
1.
This is the 1. This will be the 1. And what goes here?
-5.
-5. And that means this one would be 5. But now you might ask, well, why 80 and 90? Because. So what people do in practice and what people's programs that they provide for you to do this in SPSS or whatever do for you is arbitrarily pick plus or minus 1 standard deviation usually. So you would look at the gender difference for a medium age, a high age, and a low age. But this seems really arbitrary, right? Wouldn't it be more useful to know the points along age at which there is a gender difference rather than knowing what the gender difference is at a particular age? You can do that, and it's something that I never got taught, but I think it's very useful, which is the idea of regions of significance. So there are references for this, where this came from in chapter 2 of my book. People who rediscovered it for this purpose as well as the people who made it up initially. But the idea is that if we know the significance value for any of these simple slopes, we can turn the formula around to solve so that we can figure out the slope, the value of the predictor at which the slope effect becomes significant or not. What are the boundaries of that effect? So to be able to compute this, what you need is the variance of the slope estimate. So beta 2 in this case would be the effect of gender, plus 2 times the covariance for the interaction term that goes with age, plus the slope variance for the main effect of, hang on, nope, let me go back up. Yeah, this has already been rearranged, sorry. We want, this is the covariance of these 2 terms multiplied by age. This is the variance of that term, so SE squared multiplied by age. And so this is the part that you have to request, Cov B. I made an Excel spreadsheet through which you can calculate these things. It's in the materials that go with Chapter 2. And I also wrote a SAS program, and so I will show you how to do that. But here's the idea. So once you figure out where these boundaries lie, let's say that I have, I want to know the effective gender, and so here are my results. So this is the gender effect. So you're going to see this in the examples to follow. This is the gender coefficient at age 85. The standard error squared for that coefficient is right here in purple. The interaction term is given right here, and its standard error squared is right here. And based on that covariance matrix, I was able to find the covariance between beta 2 and beta 3 to be that number. Once you plug in those values, we end up with these 2 numbers as our boundaries. So what that means is that the gender effect, we know, is significantly negative according to this simple main effect at age 85. The interaction term is negative. So let's get some practice here. What happens to the effective age in the 1 group? What does the interaction term do to it? Which pattern is this? This is what it is. Hang on. I'm going the wrong way. Going the wrong way. Time out. So yeah, no, this is the effective age. What happens to, no, this is the effective gender. That's where I'm going wrong. This is the effective gender at age 85. What happens to this gender difference as age increases? There we go. What happens to this number as age increases according to the interaction term? This is a more negative. So if the simple main effect is negative at 85, then it becomes more negative as age increases. So the regions of significance in this case, what this tells us is that the gender effect is predicted to be significantly negative anywhere past the age of 79. Between 60 and 79, it's going to be non-significant, and anywhere below 60, it would be significantly positive. So now, rather than just asking, what is the gender effect for this age, or that age, or that age? This tells you a better way, based on your data, to think about how would the effect of gender play out in my sample? Well, if I have a sample of older adults, I may not have anybody under the age of 60. So there's no one in my sample for which a significantly positive gender effect would be. For people between 60 and 79, there'd be no gender difference. And after age 79, there would be a gender difference that favors the 0 group, because the gender difference is negative. So I like this because I feel like this is more useful in thinking about what to do with simple slopes when the values that you would plot for are somewhat arbitrary. Okay. How are we doing? So let's look at an example before going on. And we'll start with just an interaction of two continuous variables, and then we'll add some more complexity. So this is example 2b. I'm using proc mixed, but this is just a regression model. I am starting by inputting fake cases into my data set. This is a trick that you can use to help you make plots more quickly to get predicted values. So these are people whose predictor values I'm going to want to have as references in a plot later on. I'm going to add these fake people to my data set. So minus 99 is their fake ID number. I put that so that when I sort by ID, they're going to be at the top. And the first column is actually going to be grip strength, which is centered, and 3 is the standard deviation. So I put in 3 high people, 3 medium people, and 3 low people. And then for age, I put in low, medium, and high for each distinct level of that. And I'm going to add these fake cases who have 0 values on my other covariates that I'm holding constant to my data set. And I'm going to run the model on all my real cases and these fake ones. Now, you're thinking, wait, you're making up data. Is that okay? Yeah, because I'm not making up an outcome. So these cases aren't going to be used in fitting the model. But what I can do is ask for predicted values for the outcome based on the model fixed effects for my entire data set, including my fake people. And so then you have all of the plots, or the points that you would put in your plot. So you don't have to calculate them. They come standard. And anytime you revise the model, all the predictions revise too. So it's a neat trick, especially in models in which it would be very complex to write out the equation and come up with the predictions. So here's where we're at. We looked at an example earlier in the semester. It was 2A that just had this first line of the model, or this one up here. Main effective age, main effective grip strength, gender, and 2 dementia groups. Do you remember this example? So these are older adults. This is fake data, but it's generated based on real data, where we're controlling for age, grip strength as an indicator of physical function, gender, and then there's 3 kinds of dementia groups. There are people who never have it. There are people who are going to acquire it at some point during a longitudinal study. And then there's people who already, so this is the first occasion of a longitudinal study. That's the story. They have it when they start the study. So I am adding one new term to the model relative to where we left off, which is this age by grip strength interaction. Does the effective age depend on how physically, I don't want to say strong, how physically intact you are? We'll say that. Or does the effect of physical strength differ by age? Either way, you can think of it. So here's how we've come up with the simple effect of age. We take the model equation up here, and we pull out all the terms that have age in them. Beta 1, beta 6. So that means the effective age is this linear combination right here of beta 1 plus beta 6 times the value of grip strength. Go the other way to find how to get the simple effect of grip, where it's beta 2 and beta 6 this time. And the idea that we're going to be filling in these simple slopes with sort of low, medium, and high values of the moderator is then given in the estimate statements. So the first 3 lines here are asking for the effective age for different levels of grip strength. The second 3 lines are flipping it around, asking for the effects of grip at different ages. If I had not created these fake people and added them to my data set to get predicted values, here is how I would ask for predicted outcomes for every one of those 9 cases. Obviously, this is a lot of typing, but I think it's useful to point out a couple of things. Intercept. Whenever you want a predicted outcome, intercept. Anything that is not in here is being held to 0. to plot the interaction of age and grip strength, I don't need to worry about these other covariates because they don't interact with age and grip strength. So the age by grip strength interaction would be marginal, would hold for either gender for any dementia group. So I'm just going to hold those at 0 so that I can focus on the interaction, which means that those covariates are not included in these statements. You'll note the interaction term then is the multiplication of the values of the predictors for the main effects in this case. So it's the easier way to write these that you've probably been taught before in a regression class. Okay. So here's what we ended up with. I'm going to zero in on these 3 and make it bigger so we can all see what's going on. See if there's any questions. Nope, no questions yet. So you know how to interpret main effects, right? So intercept, we'll go through this quickly. Intercept of 29, for what kind of person? This is a cognition outcome for someone who is
85.
85.
Grip strength 9. They are
Man.
man.
Yeah, MW means like the order of the numbers for me. And they've never had dementia. Okay, cool, we got that much. Now, the effective gender, who's higher, men or women? Women are the 1, men are the 0.
Men.
Men are higher. Do I need to say this is the effective gender for someone who's 85 or anything like that? Nope. This is marginal. This is the gender difference among any kind of people, according to this model. Likewise, this is the difference between people who have no dementia and future dementia and no dementia and current. And if I wanted to know the non-referent group difference, I'd have to subtract these 2 betas. But these are also unconditional. They're for anybody. So I can talk about this as the effect of age, not only after controlling for grip, gender, and dementia, but it's also specific to what kind of person. This is the simple or conditional main effective age for what kind of person because of my interaction term.
So grip's at 9.
Grip at 9. So it's not just holding grip strength constant, it's holding it constant at 9. That's the difference. The rest of these, you can just say constant. So if we talk about this as the effect and grip as the moderator, so for every year older you are, what happens to you, according to my simple main effective age? Yeah, lower. This is a main effect, so you can just say up or down, right? Cognition is expected to be lower by about 1/3 of a point for every year older you are. Now that effect is specifically for someone with a grip strength at the centered value of 9 pounds per square inch. According to the interaction term, what happens to this age effect, you highlight that row and the interaction term, as grip strength increases? Which pattern is this? Less negative. So for every pound of grip strength, this coefficient for age becomes less negative by 0.12 per pound grip. So can you think of a nicer, more friendly way to say less negative?
More positive.
Nope, that's not the same thing. The effective age is negative. But what does less negative mean? Is it becoming weaker or stronger? It's becoming weaker, right? Less negative means it's getting closer to 0 as grip strength increases.
It's lower or less.
Yeah, so I would say that the effective age is diminished in persons with higher grip strength. The effective age is less deleterious, or something like that. Age matters less if you're stronger. Age is less bad for you if you're stronger. How's that one? That captures the negative, right? That's what less negative means.
Wait, so would this model say with a certain amount of grip strength, age would have a positive effect?
Yes. If it's going to come down, or on the number line, it's going to come to the right? It's heading towards 0, and it's going to keep going. So in super duper strong people, age is good for you. The question is, do we have any people that strong in our sample? We might want to know at what point the age effect becomes non-significant, right? How strong do you have to be? That's a regions of significance question. So here are a couple examples from our estimate statements. The age effect in the middle is the one that was given to us by the model. That's the simple main effective age because it's at grip equals 9. So you can see that it becomes less negative as grip increases. And for somebody who's 1 standard deviation above the mean in grip strength, so they're at 12 pounds, the effective age is non-significant. For somebody who's weaker, 1 standard deviation below the mean, the effective age is still significant, as you might expect. It's even stronger. So this pattern then, this lends itself to the idea of regions of significance. It's like, well, it's significant at 9. At some point between 9 and 12, it shuts off, right? It becomes non-significant. What point is that? And then eventually, if we kept going, like grip strength of 100, it's going to go to positive because it's non-parallel lines. In thinking about the nature of the interaction, you'd want to know at what point it flips to positive and if any people are actually in your sample with that level. Let's go the other way. Now what if the story is about physical capability and how that depends on how old you are? So this is the effective grip strength, holding constant sex and dementia group, and holding constant age at 85. So for every pound you can squeeze on this device, your cognition is predicted to be 0.6 higher. That's if you're 85. What is this slope? What does the interaction do to the slope in older people? What's the pattern? This is a more positive. So the effect of grip strength becomes more positive by 0.12 per year of age. And in English, being stronger matters more in older people. Age enhances the effect of grip strength. Age exacerbates the effect of grip strength. Think of all the words you had to learn for the GRE. Get them back out again. There's lots of ways to say more positive that make more sense. Once you figure out what the 4 patterns is, you can wordsmith it however you want, but making sure you're in the right pattern. And so then we asked for what the predicted effect of grip strength is at different ages. The middle one, again, is what's given by the model here. That's at 85. As age increases, the effect of grip strength, it becomes more positive. As age decreases, it becomes less positive. And somewhere between 80 and 85, it becomes significantly positive, but we don't know where. After 85, we know it's positive and significant. And these are the predicted values that the estimate statements provided, or these same numbers would show up in your data set. If you had added, let me point out this command that I don't think we've used yet, this right here. So there's 2 new commands on here that you haven't seen yet. Cov B gets you the asymptotic covariance matrix that you need to calculate regions of significance. And this one, out PM, that asks SAS to take your current data set and create new columns for the predicted outcome from the model fixed effects and its standard error. And it appends those to your data set and saves your data set as a new name, and you list the name right here. So this data set, pred age grip, is a copy of my original data with new columns for the predicted outcomes from the fixed effects. So sitting at the top of it would be the 9 fake cases that I put in there. And so I just take out those 9 values and go plug them into Excel or R or whatever my favorite graphing package is. And so I just printed that to show you that those numbers are exactly what you would get if you ask for it in a data set versus writing it out yourself. And here's the pictures. So I decided to make the effective age the predictor in the picture and to plot different lines for different levels of grip strength as the moderator. In the book, I have another picture that goes the other way too. So the middle square right here, where my cursor is right here, for years 85 and grip 9, that's my model intercept. This is the "you are here" sign right here. The slope of the line for age, that's the main effective age that's given by the model. The vertical distance at 85 as a function of grip strength, that is the main effective grip given by the model. And your interaction, you can think of either way. You can think of it as how this vertical difference shrinks or expands as a function of age. Or you can think about how these slopes become less negative or more negative as a function of grip. So the estimate statements told us if there was a significant slope here, here, and here, as well as a significant vertical difference here, here, and here. Here is Cove B. So this is not something you typically need to ask for, but this is the asymptotic covariance matrix of your fixed effects, where the diagonal is the standard error for each of your fixed effects squared, and the covariance between your fixed effects is given in the off diagonal. The macro that I wrote takes this input, does the calculations for you if you tell it what your predictors are and the centering points of your predictors, and it outputs this interpretation. So in this case, if the effect of grip is what I'm asking for, these are the numbers that we saw earlier. The effect of grip strength is going to be significantly negative below age 70, non-significant between 70 and 82.7, and significantly positive after 82. So somewhere we said between 80 and 85 is where the effect of grip strength became significant. I just found out that it's 82.7. So anywhere below 70, age 70, it will be significantly negative, non-significant from 70 to 82, and significantly positive after 82. If I go the other way, run the same macro, now switching out the predictor and the moderator, I get the values of grip strength for which there is a significant effective age. So the effective age is significantly negative anywhere below 9.6 pounds. So remember, 9 was my centering point. It was near the mean of the sample. So about half my sample is expected to have a negative effective age. It's non-significant between 9 and 18, and the effective age is significantly positive after 18. So you wouldn't think that age is good for you. The question is, do you have anybody who's that strong where that would actually apply? So you'd want to look at the distribution of your covariates to figure out how much of your sample is expected to have neutral, positive, or negative effects.
And as an outcome, if we would want to train people to try to have strength at that level?
Well, yes, whether or not this is a causal effect is a whole separate course, but yes, that's very strong. Yes, whether or not they get smarter if they go to the gym, I have no idea. But, cool, huh? How do we feel about this? Yeah? Is cool? Do you feel like this is stuff that is new to you, or just like you're trying to stuff that you had seen before and now are trying to remember?
I've seen it before, but I haven't had it laid out quite piecemeal like this before.
Yeah?
It's like more detailed and more information provided.
Good. Yeah, so this is, besides age and grip, if I want to know if my control group changes differently than my treatment group, right? That's a question you might answer in longitudinal data. That's a group by time interaction. So all of this is relevant. What if you have a quadratic change in your model and you want to know if your group has a different quadratic rate of growth too? That's a three-way interaction. That's group by time by time. So that's what I'm going to show you next, actually, is how to do three-way interactions as well. Dun, dun, dun. Don't be scared. You know what they do? Three-way interactions take your two-way interactions and make them, say it with me, more positive, less positive, more negative, or less negative. That's it. That's what they do. Three ways adjust the two ways adjust the main effects, and the main effects predict your outcome. It's like a trickle-down thing. Questions? All right, well, have a great weekend. Hope to see you all on Tuesday, and hope everyone else out there has a nice conference. And that's it.